Hey, good evening. Welcome back to AP Stats Notes Online. Want to finish up section 2.2 here, finish up chapter 2. We spent the last couple of days getting really familiar with Table A, normal distributions, how to calculate the proportion of individuals that are in a particular distribution using the area under that curve. We need to continue talking about what we're doing when we're finding these values in Table A and when we start using or the empirical rule or your calculator. So I'll try to make sure that we keep discussing what those numbers mean because it's very easy for those to start losing its meaning. Anyway, what we want to talk about today is, one, how to take your very non-specific, contextless Table A and use that in the context of a stats problem. In other words, how we want to use these to do calculations. And this does involve your four-step process again. Remember, your state plan do conclude. So if we're going to use this to do some calculations, we got to make sure that, one, we're showing all the work we need and that we understand what we're doing as we do it. So your state process, we're going to express the problem in terms of the observed variable x. We want to make sure that when we state what it is we're looking for, that we do it in context. Next, we want to plan, and part of our plan here is to draw a picture of the distribution and shade the area of interest under the curve. We're going to keep drawing curves and shading the area that we want. Obviously, your due phase is just, you're just going to do the calculations. Now, part of doing your calculations means that we're going to standardize the x values. We're going to standardize the values of the variable that we're working with so that we can get into Table A. The only way we get into Table A is if we have a set of z-scores. I mean, that's what we mean by standardize. And then we're going to use Table A to find the area that we're looking for. And then, of course, in any good stats problem, we have to have a good conclusion. What does it mean? What does this number mean in the context of a problem? And we've got to make sure that we include context. Table A doesn't give you that, the problem does. Okay? So, let's take a look at an example of what we need to do through this process. Okay? So, when Tiger Woods hits his driver, the distance the ball travels can be described by a normal curve where the mean is 304 and the standard deviation is 8. And those are in yards, 304 yards to 8 yards. Okay? What percent of Tiger's drives travel between 305 and 325 yards? Now, this could be very, very useful information for Tiger if he's getting ready to tee off. I don't know if you guys know anything about golf at all, but anyway, when he starts to tee off and there's a bunker or a pond or a water hazard that is, 310 or 15 yards out from the tee box, he's got to start making a decision. Should I hit my driver or should I back off and hit a lesser club so that I don't run the risk of getting myself into trouble? So useful information. So how we want to go about working this problem? Well, again, we're going to follow our four-step process here, and we'll do that as soon as I find a board that works. Always an issue. So, I don't want this. We need to state, right? What is it that we're trying to find? Okay? So we're going to let, and part of this state process is us starting to define our variables, right? We're going to actually start using variables to mean stuff. So x is the distance, so I'm going to let x be the distance in Tigers drives. And I want to use X here because it allows me to use some symbols that are going to make a little bit more sense. Okay. Distance, not in, maybe of would be a better word, but of Tigers drive. Okay. And here's what we know. We know that his drives are normally distributed with a mean of 304 yards and a standard deviation of 8. Okay. So what we're trying to find out is the percent of Tigers drives that are between 305 yards and 325. Okay. So let's plan this out. Well, it's going to be really helpful to shade a curve, and this can be part of showing your work, and I'll explain that more in just a second. So the mean is 304. I'm going to go ahead and list out some standard deviations here. See, this is 312. Second standard deviation is 320, and this is not very accurate, but whatever. So 328. Then we're going this way. We're at, not 296, and then 288, and then 280. Okay? And we're trying to find the proportion of his drives that are between 305, and so 305 is going to sit about right here, to 325, which is going to sit about right here. I shade this curve again because I want to make sure my answer makes sense. Okay? That's what we're looking for. All right, well, great. Let's go do this. Okay? So do. All right. Well, I cannot find this proportion. I cannot find the area. I cannot find the proportion of his drives that are between 305 and 325 until I get into Table A. And I can't get into Table A until I have some z-scores, right? Table A is all standardized values. So I got to find the z-score. So I find the z-score of 305 by taking 305 minus 304 and divide it by 8. And I got to do the same thing for 325. So I take 325 minus 304 and divide it by 8. Okay? When I do that, my z-scores become 0.13 and 2.63. I think that's right. Okay? Great. Now I'm trying to find the proportion of drives. Now it's a matter of finding the proportion of z-scores between 0.13 and 2.63. Okay, but what I do want to take just a second to make sure that you understand is that this z-score corresponds to this distance, and this z-score corresponds to this distance. These z-scores actually have a meaning. Okay? All right. That being the case, then we've got to get into Table A and start trying to figure out how to piece this together. Okay? Now, it's like our intervals from our homework from before, right? If I go and find 2.63, that's going to give me the area, or it's going to give me the proportion of his drives that are strictly less than, right? Well, I don't want strictly less than. I want this proportion to be cut off at 305. So we're going to end up subtracting two values, right? So let's go do that. All right, so I need some values here. So I need 2.63. So I need Table A at 2.63. 3 column is here. 2.6 is here. So that's 0.9957. Okay? So, to find this, I will take 0.9957 and subtract from it. Now I've got to go find 0.13, and I won't bring this back up. I'll let you follow along, but 0.13 should get you a value of 0.5517. I'm going to subtract 0.5517. And when I subtract those values, and I'm going to bring this over here, so now the proportion of z-scores that are in this interval becomes 0.4440. Okay? Well, since 0.13 corresponds to 305 and 2.63 corresponds to 325, then that means the proportion of Tiger's drives that are between 305 yards and 325 yards is approximately 44.4%. So a little less than half the time, he drives the ball between 305 and 325 yards. So, you know, if there is a bunker or a water hazard that's, in that interval out from the tee box, then he might want to consider backing off a little bit and taking that out of play. Okay? So that's our plan. That's our plan and our do. We need a good conclusion, and I kind of already said it already, but what you'd want to say is about 44.4% of the time Tiger drives the ball between 305 yards and 325 yards. Okay? So this is how our table A, how we can add some context to our table A, and how we want to get into table A to use this. Now, I do want to take a couple of seconds here and show you how the calculator can do this for us. Okay? Let me do that. You have your calculator. Bring that guy up. And here's where you want to go. Okay? Normal distribution. This is a normal curve shows the shape of a distribution. And I make a big point about that because if you look right above your VARS button, there's DISTR in blue. That stands for distribution. So anytime we get into a particular type of distribution, we want to get into that menu. So you hit second VARS, and there's all of your different types of distributions. Now, you've got two options here for normal. You've got normal PDF and normal CDF. Normal PDF will take the actual formula for the normal curve and do calculations based on that particular integration. We aren't going to use that. In other words, so long and short of this is we're never going to use option one. We're always going to do normal CDF. Okay? So you bring up normal CDF, and you 83ers are probably looking at just normal CDF with a parenthesis. What it's waiting for is for you to put in the lower bound, right? And this is where shading your curve comes into handy also. Your lower bound means where's the lower part of your area here. So in the Tiger Woods problem here, the lower bound of our shaded area is 305 yards. The upper bound is where it cuts off, where it stops, 325 yards. And our mean and standard deviation, we can actually plug in the mean and standard deviation from the problem. Again, in his drives, his mean is 304 yards, and his standard deviation is 8. So 304, that's our mu, and 8 is our sigma. Right, and then we hit paste, and 83ers or any 84s that don't have their operating system updated should be looking at this. You need to type in lower bound, comma, upper bound, comma, mean, comma, standard deviation. And when you hit enter on this, it will give you the proportion of his drives that are between 305 and 325 yards and make your calculations a little bit shorter. Now you don't have to get into Table A if you don't want to. Okay? Compare the 44.5929 to what we got here, which was 44.4. So it's a little bit different. Again, it's because the calculator can be a little bit more accurate. Either way, Table A in your calculator is going to be just fine as far as recording an answer to this, okay? So anyway, that's how we use our normal curves in a stats problem. And if you're going to use the calculator, which means you do not have to do these z-score calculations because now you don't have to get into Table A, you still need to shade a curve. This is how you show your work. Draw a curve, shade the area that you want. That's how you show your work, okay? We can talk about the calculator a little bit more in class as far as how to use it as we need to. I would rather, for right now, you guys get in the habit of using Table A. If the calculator makes sense, just make sure you shade a curve to show your work, okay? So let's move on from there. There is a check your understanding on page 124. There are, you have to refer to the examples on pages 121 and 122. It talks about the cholesterol levels of young boys. And that's another normal distribution that we use, 14-year-old boys, it looks like. So take a look at the check your understanding there and see what you come up with. Maybe we can use this to talk about your calculator a little bit also. All right, and do pay attention. Number 3 does kind of jump examples on you. We're back to Tiger Woods and his drive lengths. So make sure you're paying attention to that and finding the 80th percentile there. And that's a situation where you're going to want to work backwards, right? And we did that in the notes from a couple of nights ago in the other note packet. We can go through that again in class if we need to. Okay, but give them a shot, see what you come up with, and we can move on from there. Next, how do we know if a distribution is going to be normal or not? How do we know if a normal curve is the best density curve to use to show a distribution? Okay. Well, there's some strategies we can use to help us figure that out. Number 1, we're going to plot the data. That's always the first thing we're going to do. We're going to take our data, we're going to plot it out and see what that distribution looks like. It needs to be symmetric, roughly symmetric, and hopefully we can get a sense of whether a bell curve is going to fit that or not. Okay, so we can make a dot plot, a stem plot, a histogram, whatever, and then I don't know if this box is coming through on the notes or not about the microphone capture is on. We'll find out in a minute, but if it is, in your notes it says the next thing you want to do is to check whether the data follow the empirical rule, right? So now that you have your data plotted, you want to go find, and this is going to involve calculating the standard deviation, right? We have to go find the standard deviation, find the mean and standard deviation, and then once we have that, and we know what the values are for being 1 standard deviation away and 2 and 3, then we need to go and count the number of observations that are within the first standard deviation and see if it's pretty close to 68%. Do the same thing for 2 standard deviations and make sure it's close to 95% and so on and so forth. We want to make sure that we go through and do all of that. Now, there are some software packages that will make this work a little bit less tedious, because that could take some time, right? If we're going to count observations and make sure that 68% of them are within one standard deviation of the mean, that could take some time. So we do have another way of trying to figure out if a normal curve is the best curve to show this distribution, and it's something called a normal probability plot. This is something that your calculator will do for you. And so quite simply, for a normal probability plot, what we're looking for is a plot that is pretty close to a straight line. The plot then will indicate that the data are normal. Systematic deviations from the straight line indicate a non-normal distribution. Now, what we mean by systematic is if there's a tendency towards a non-straight line, to a curve, then we're going to assume that the data is not normal. Outliers appear as points that are far away from the overall pattern of the plot. Okay. So, for example, and we can type one in our calculator in a second and figure out if a distribution is going to be normal or not. Okay. So here is a histogram that shows the survival times of a guinea pig that were injected with an infectious bacteria. This is a medical experiment that was carried out. This is in the example on page 127. So there's the survival times, the number of guinea pigs that survived at different day lengths on the left. And then from that histogram, we would have the actual data. And so we would let the probability plot show us if this data can be normal or not. Now, obviously, the histogram shows us this is not going to be a normal distribution. Okay? What a normal probability plot does is it takes the values of the variable, right? So you see the horizontal axis is the same. So we take the guinea pig that survived, probably 50 days, and we calculate that 50 days into a z-score. So this value this dot right here represents a guinea pig that survived a little less than 50 days, and then that guinea pig fell a little over 2.5 standard deviations below the mean survival time, because his z-score is negative 2.5. It looks like it may be a little bit higher than negative 2.5. So it plots an individual's value against its z-score, against its location in the distribution, right? So since our histogram bars are pretty tall here in our lower survival times, 100 days, in between 0 and 200 days is where our tallest bars are. That's where the densest collection of dots are, right? All of our guinea pigs are falling right here. There's a lot of them, right? And what you also get a sense of is in relationship to the mean, and the mean is at 0, right? If a guinea pig falls at the mean survival time, then that z-score would be 0 for that guinea pig, right? So maybe we need to make a note of that. So a guinea pig that falls right here, this would be the mean survival time. So these dots, there's a big collection of dots that are really close to the mean, right? And then it starts to curve, because as it starts to curve, our larger values don't get quite as far away from the mean as fast, right? Our lower values, so our mean is probably going to be somewhere right in through here, or maybe right in through here, right? So it hopefully makes sense that our lower values, even though our histogram bars are taller there, they're going to be a little bit further away from the mean. That means all of these guys, while they're more spread out, and that's represented by these spaces, so our guinea pigs are spread out here, but they aren't deviating from the mean as quickly. So that's why this thing starts to level off and creates this curve. So anyway, this normal probability plot shows us that this is not going to be a normal distribution. We knew that just from the histogram. Okay? We'll go back. I want to go back and type in how to use a normal probability plot, and we can do that in just a second. We'll be done with the notes. This is just showing you that the next chapter we're going to talk about is regression analysis, scatter plots and correlations. So we'll talk more about that later. Okay. let's talk about your normal probability plot a little bit more. So that was for the collection of guinea pigs. Let's try something else. Another example in your book, and this example walks you through how to actually count the data points and to make sure that 68% of the data values fall within one standard deviation and 95% of your data falls within two standard deviations, where you have to go find the mean and the standard deviation and actually count the data. I'm not going to do that. What I would like for you to do instead is take a couple of seconds and type these into your calculator. Type this into a list into your calculator. And then you can restart the video and I'll show you how to do your normal probability plot. Okay? All right, so all the data is typed into a list, right? So first thing we can go do is hit second y equals for our stat plots. Make sure that you have the first plot turned on. You could do a quick histogram. And my data is in list 1, so I'm going to change that. I need to get rid of my frequency and make that a 1. And graph that, zoom 9 it, and that's not very good, but my guess is this is not going to be a normal distribution. This is a terrible, terrible window for this, but I don't want to take the time to adjust it. We talked about that before. So instead, let's go into our normal probability plot. If you go back into your stat plots, your normal probability plot is going to be this last guy out here. Okay? Looks like a straight line there. Okay? Your data list is in list 1. Your data axis is going to be the x-axis. We can mark it with pluses or circles or dots or whatever you want to do. We can just mark it with whatever, right? I'm going to zoom 9 that guy. Okay? And there's your normal probability plot. And as a matter of fact, that's a pretty straight line, not very curved at all. So, we actually probably could fit, which means that our histogram window was really terrible. Didn't give us any idea of the true shape at all. But, and it might be because of this point out here. I wonder if I typed something in wrong. I might have. But anyway, pretty straight line means that our distribution is roughly normal, and so we can use our normal calculations with this particular situation. Again, going back to this example of unemployment rates in the 50 states in November 2009. That example is pretty good about walking you through how to make sure that 68% of your unemployment rates are within the first standard deviation and so on and so forth. But we also showed how to use the normal probability plot here to talk about the same situation, whether this is normal or not. Okay? If there are any questions on that, we can talk about that a little bit more in class. Don't forget about your check your understanding. That's on page 124. Get that worked. We'll talk about those in class as well, and then start working towards our test, which is looking to be next Wednesday.